And we continue talking about the two-variable regression analysis, and today I would like to discuss something very important, which is interval estimation and hypothesis testing. From this slide you can get the quick overview of today's lectures. First, I will start with normality assumption, which is very crucial for being able to undertake interval estimation and hypothesis testing. Then I will move to the parts related to interval estimation, followed by hypothesis testing, and in the end I will show you how you can evaluate your results. So let's start with normality assumption for the error term. During the previous class I discussed something like classical linear regression model assumption. There have been 7 of them. And today I would like to add the 8th assumption, is that the error term or the disturbance term is normally distributed. And let's see what is meant by normal distribution of the error term. First of all, the mean value of the error term should be equal to 0. So when we sum all the error terms and divide them by the number of the error terms, in the end we should get the value of 0. The second property is related to the variance of the error term. It must be equal across all observations. In a sense, it must be constant. So it should not be changing from one observation to another. And the third property is related to the covariance. So the error term from one observation should not be correlated with the error term from another observation. So the correlation coefficient between the error term 1 and the error term 2 should be 0. At some moment I think you will see a notation like this. So those are the assumptions. They can be more compactly stated in the following way. So the error term followed by the symbol, which means distributed as, where n stands for normal distribution, and in the brackets we've got that 0, which stands for the mean value, and sigma squared, which stands for the constant variance. To account for the third assumption, we can amend the previous notation a bit by adding NID instead of n, where NID stands for normally and independently distributed. So this independently distributed comes from the third assumption. Given the normality assumption, given that the error term is normally distributed, Euler's estimators now have the following properties. So as before, they are unbiased. That means that the average value is equal to the true population value. So this is what I told you before. If we take, a lot of samples out of the same population, calculate the coefficients, and then when we average them, in the end they should converge to the true population value. So this mean value should be equal to the true population value. Besides that, the OLS estimators, beta coefficients, they have minimum variance, or in other words, they are efficient. So they have minimum variation. And the next property, I believe this is something new we haven't discussed before, is that OLS estimators are consistent. So as the sample size increases, so as we add more and more observations, the estimators, the coefficients converge to their true population value. So in other words, the bigger the sample, the better, because our coefficients converge to their true values. And the last two properties are related to the normal distribution of the intercept and the slope coefficients. So the first notation stands for beta 1 being normally distributed with constant mean of beta 1 and constant variance of sigma squared beta 1. And beta 2 is also normally distributed with constant mean of beta 2 and constant variance of sigma squared.